All right, ladies and gentlemen, we are going to start our new chapter here on probability. And I'm telling you now, my kids are running around, my dog is running around. You may hear them in the background. You'll be okay. So, our first topic with probability is on what we call counting outcomes. And we will start that with a story. Joe has chosen one lucky lady to accompany him to dinner this weekend. Who is that lady, you ask? That is for Joe to say. Anywho, Joe is planning a spectacular evening. The period is missing. The night will kick off with Joe and his auntie picking up his date, where he will give her 1 dozen roses. He's romantic. Then it is off to the theater, where they will see I Still Believe. And then Joe has decided to take his lovely lady to eat at the greatest restaurant known to man, Chili's. Now, Joe has chosen to go to Chili's, besides the fact that it's great, because they have what's called the 2 for $20 dinner for two. You get an appetizer to share and 2 full-size entrees for just $20. And since he's already spent all the money on the roses and the movie, he doesn't have a lot of money left. So if I scroll here, we can see the possible appetizers and the possible entrees. Maybe I can't scroll. There we go. And Joe's decided that an extra added benefit. He enjoys this dating thing. He seems to think that there are enough combinations here that he can go on many, many dates and still not reach every possible combination of appetizers, his meal, and his date's meal. And so our goal here is to figure out how many possible different ways Joe and his lady friend are able to make an order from this 2 for $20 menu. Now, if we were in class, I would give you guys some time to play through this and struggle, and then we would talk about what happened, but I am going to do that struggle for you. So if I don't know how to figure this out, I'm going to start by saying we have 1, 2, 3, 4, 5 different appetizers. And then I'm going to count and say there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different entrees. I figure I need to know how many different appetizers and entrees there are for me to figure out how many different combinations there are. All right, I clipped that in from the previous page to kind of help. I'm not going to remember what those things are. So I seem to remember learning about tree diagrams in grade school, and I'm going to start trying to make one and see what happens. So we can go spiced panko onion rings. We can go fresh guacamole. We can go salad. We can go the Texas cheese fries. Or we can go chips and salsa. All right. So we only get one appetizer. And then if I look at just one of those and say that's our first choice, and the next choice is what do I get? And I could get a classic bacon burger. I could get fajitas. I could get the mango chili chicken. I could get the salad, grilled at 2 salads, grilled chicken salad, and so on. And that's just my choices. So it's already becoming apparent that this is going to take a long time going through this, because there's 5 choices originally, and then I have 1, 2, 3, 4, I have 12 choices, regardless of what original choice we made. And then my date, or Joe's date, has 12 choices after that, and we start to see that there's a lot of branches. And so if we're going to name possibilities, we could just say maybe Joe chooses the Texas cheese fries for him and his date, and he chooses to get the fajitas, and his date chooses to get the half rack of ribs. They could have also chosen together to get the cheese fries. Joe may have still chosen the fajitas, but his date may instead have chosen the crispy chicken crispers. And that is a separate choice in terms of the decision that could be made overall. So obviously, we have a lot of different options for combinations, and there has to be a better way to do this. And we'll come back to this a little later and get more specific with it. But if you think about, I have 5 groups originally. I have 5 choices. And then off of each of those groups, I have 12 choices for Joe. And then off of each of those groups, I have 12 choices for Joe's date. And we can see that that's going to give us a very large number in terms of the total number of choices that can be made. That ends up giving us 720 possible combinations. And we'll see that this connects with probability overall, because when we talk about probability, we're always going to compare to some total number. And so in this case, the total number is 720, and when we get to probability, that would be our denominator. All right, so let's look at some vocabulary associated with these concepts. Each of these single results is called an outcome, which I can't spell apparently. And the list of all possible outcomes is called the sample space. So if you think about the situation where Joe and his date got the Texas cheese fries, Joe got the fajitas, and his date got the half rack of ribs, that is a single outcome. If I were to sit there and make the entire tree diagram that represents all of those choices, that giant list would be the sample space. Each of the different decisions being made is called an event. And so in the Chili's situation, there was an event, which was choice of appetizer. There was an event, which was Joe's choice. And there was an event, which was the choice of his date. We will continue to use these words as we go forwards. All right, let's continue with some vocabulary, etc. We have 2 main terms here. We have what's called an outcome, and we have what's called a sample space. Here we have a spinner that just has two sides. It has red and blue. And if we look at the situation of spinning the spinner twice, and we say we get a red and then a blue, we call that an outcome, because that's only one possibility of what could happen if I spinner twice. Getting red and then blue is one situation. If I make a list and say, well, I could get red and then red, I could get red and then blue, I could get blue and then red, or I could get blue and then blue, we would call this a sample space, because it is the list of everything that could possibly happen when you spin this spinner twice. All right, so let's look at some more examples for outcome and sample space. Rolling a number cube 3 times. Number cube is a die, but dice can have more than 6 sides. They don't have to be cubes, as we'll see later, so they call it a number cube. If I roll a 5, and then I roll a 2, and then I roll a 2, we would call that an outcome, because that is only one of the possibilities of what could happen if I roll a number cube 3 times. You could get a 1, and then a 1. You could get a 1, and then a 2. You could get a 6, and then a 2. There's a lot of different things that could happen. All right, so moving on. If I throw a coin 1 time and I have a list that says heads and tails, we would call that the sample space. You cannot throw a coin 1 time and get both heads and tails. You can get heads or tails, and that's it. And so heads, tails is the entire list of possibilities. If I toss a coin twice, we have more possibilities. I could get heads then heads, I could get heads then tails, I could get tails then heads, I could get tails then tails. And so this is also a sample space for that situation of tossing a coin twice. If I choose cards from a deck, which by the way, there are 52 cards in a standard deck, we may need to look at cards later on in this chapter, and we will include a type out of a deck of cards, because I know not everyone knows what is in a deck of cards. But if I choose 5 cards and I get a 4, and then a 10, and then a jack, and then a 3, and then a 7, that is a single outcome, because it is possible that I get a 2, a 2, a 2, a 3, and then a queen. It's possible I get a 2, a 2, a 3, a 2, and then a king. There's a lot of different possibilities, and so 4, 10, jack, 3, 7 is only a single outcome. All right, so as I go through a couple more examples, we're going to talk about that vocabulary and make sure that you're okay. If we think back to our chilies situation, and we saw that a tree diagram was going to take forever, and I had to think about how the numbers were being grouped. That process of multiplying is called the fundamental counting principle. Or FCP. So if we look at this situation of going to an ice cream parlor where I have 3 choices of ice cream, 2 choices of topping, and you have to make a decision on whether or not to get whipped cream, we can figure out the total number of choices by making a tree diagram or by doing the fundamental counting principle. So if I make a tree diagram, I'm going to start with the fact that I can get chocolate, I can get vanilla, or I can get Rocky Road. And off of that, my choice is topping of, get out of the way, chocolate or butterscotch. If I get vanilla, I could also get chocolate or butterscotch. And if I get Rocky Road, I could also get chocolate or butterscotch. Each of those brings with it another choice, and whether we are going to say yes or no to whipped cream. And so, as you can see, this quickly gives us a whole lot of different choices as we branch off. And let's just talk vocab again real quick. So the entire list here is called the sample space, and each of these branches is an outcome. So if I chose to get vanilla with chocolate sauce and yes, whipped cream, this one pathway is an outcome. If I look at the different rows that I wrote, and say I chose an ice cream, that's event 1. I chose a topping, that's event 2. And I chose whether or not to get whipped cream, that's event 3. So if I'm going to do the fundamental counting principle, I don't get a list of all of the possibilities. I only get a total number of possibilities. And the way the fundamental counting principle works is you multiply the number of options in each event. You do not necessarily multiply the number of events. So I have 3 choices in event 1. I have 2 choices in event 2. And I have 2 choices in event 3. If I do 3 times 2 times 2, I get 12 possible outcomes. And if I go up and count the number of branches, you'll see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total possible outcomes. So I'm not going to follow the directions here. Fundamental counting principle. Here, I'm going to do 3 times 2 times 1, 2, 3, 4, 5. And that gives me 30 possible outcomes. Again, number of items in each event, or number of choices in each event, not the number of events. Problem 4 says to make a tree diagram, and I'm not going to do that because I want to show you what number is not being used. There are 3 events here: type of mineral, texture, and color. And yet we will not use the number 3. There are 3 events, but we're not using 3. It is the number in each event, not the number of events. I have 4 choices in event 1. I have 2 choices in event 2. And I have 2 choices in event 3. 4 times 2 is 8 times 2 is 16. If I made a tree diagram, which I'm not going to, there would be 16 total outcomes. All right, the following is going to be turned into a class kick, which you will complete. And that way, if you have questions, if your teacher needs to help you, he or she may do so. Again, you will not be completing this through Google Classroom. You will be completing your classwork through ClassKick. You'll hear from me soon. Have a good one.